we have to have that F parallel has disappeared. Everything is sloshing around and finding its place. But when the charge polarization is established, by definition, F parallel has to disappear. So F parallel has to go to 0 when the equilibrium is reached. Otherwise, they're still sliding around finding their spots. And that must mean, of course, that E parallel has to disappear, which by definition means the entire field has to be perpendicular to the surface. So we have basically reasoned why that must be. Once the charge polarization has been established, the only remaining pole that can be on the charge polarization is perpendicularly out from the surface. And since it can't actually do anything with that, we're in our final equilibrium state. So therefore, the entire net is perpendicular to the surface. So let's go ahead and make a sketch. We'll make a sketch where we combine the uniform external electric field with this dipole-like charge polarization. So I guess I'll put a big plus sign to indicate I'm going to add this field and this other field, which looks like this, which the field looks like this. Kind of already drew it over there, but it's nice to see them separate. So what does that end up looking like? Oh, and I don't know why I didn't, but I can certainly draw in the object. It makes it look a lot nicer. So what do you get when you do the vector sum of these two? So E external plus E induced. That's E induced. Here's what the whole drawing looks like. That's what the field looks like overall. So first of all, features. Notice that I did not draw any field lines in the interior. That's because the net electric field there is 0. If you want, you can just put a big 0 in the interior. Or you can just remember there's no field lines there, so there's no field there. We see that out here, E net is basically looks like E external. And that's just simply because we're far enough away from the local influences of this conductor that the field overall basically has just returned to looking like E external, because being uniform, of course, it never dies. So that never dies, but when we get far enough away from the conductor, that field starts to be negligible. So you find that on the far left and far right edges, the field starts to look indistinguishable from E external. But what you see is close by, but still outside of the conductor, where you have both influences. You have a E external, but you have a heavy influence from E induced. It bends the field lines perpendicular to the surface. And I've tried to draw those as right angles as best as I can. And in case I can't draw very well, I labeled them with right angles. Okay? So near the surface, near the outside surface, the net electric field is bent perpendicular. And again, you can think of it if you want. You can draw in the forces that are on those mobile charges. This, all it remains is a force perpendicularly out from the surface. It can't do anything with that, so it's a happy place. It's not going to move anymore. This and this also. The only remaining pull they have is just directly against the inside wall, and since it can't actually jump off the object, it's settled where it's going to be. The musical chairs of charge polarization are all done. And this happens very rapidly, so that's the end result. Are there any questions on that? Okay, so let me give you a practical usage of this as well. So just so this doesn't get too abstract, let me give you a practical usage of this idea that electric field lines get bent perpendicular to the surface. So imagine that instead of having this kind of spherically shaped conductor that I've been working with, let's make it be a sphere with this big spike on it. So I have this weird shaped conductor with this spike, and let me go ahead and put in this external field. Let's say it's uniform. And then when you approach the object, in having to bend perpendicular to the surface, so on and so forth, so we make sure that the field returns to the uniform look far away to either direction. But then close by, what you see is once again, that the conductor bends the net field lines until they're perpendicular to the surface. Where do you notice is the largest electric field? Strongest electric field? It's here, right? It's at the spike. So here, we get a very strong electric field. Now, if this idea of the field lines having to be bent perpendicular to the surface doesn't convince you of that, it seems kind of like a non-explanation to say that the field lines have to be bent perpendicular to the surface and that just the geometry means that they have to get closer together. That's not a very satisfying explanation for why the field is stronger. Here's another explanation. We can draw in the charge polarization. So there's minus here and there's plus here. And one of the rationale we can give to why the electric field is so strong near the spike is that the charge polarization, in adhering to this crazy geometry, means that it puts a lot of minus charge on the surface of the spike, right? So the reason why E net is strong here is simply because the E induced has a much larger contribution there. So what is this good for? This is a lightning rod. So you may know that they put these big spikes on the top of buildings to protect against lightning strikes. So perhaps you know that if they get struck by lightning, they have a wire that runs down to the ground so they can disperse that extra charge instead of having it do any damage, right? But what you may not realize is that a lightning rod is not just there in case. It's actually more likely for lightning to hit a lightning rod, okay? It actually attracts lightning. And the reason why it attracts lightning is the tearing apart of air molecules. Where is it likely to get torn apart first? Where the field is strongest. So it can actually cause what's called a streamer, which is this region of strong field where the air molecules start getting torn apart first. And that gives something for the lightning strike to connect to, okay? So lightning rods are not just there just in case. It's more likely for lightning to hit there, okay? They attract lightning. You will find this on all sorts of buildings. I posted some photos of the big lightning rods on the Eiffel Tower that I took on vacation one year. These big kind of bundles of spikes. Basically, any kind of sharp corner tends to have strong electric fields. So if you don't want strong electric fields, you want to make it as rounded as possible, okay? Are there any questions on that? Okay, so that covers the conductors quite a bit. I have one more entry in the row here, but before I do that, I don't want to let the insulator fall too far behind. So let me catch up the insulator. Any questions before I do that? Okay, so let's talk about the insulator. So the charge mobility is not there, okay? All right? So you may think that it is shut out from participating in any of this phenomenon. So we might have, say, a positively charged nucleus, and is surrounded by a cloud of electrons. It may be that the center of mass of the electron cloud is coincident with that of the positive charge, and this thing has no permanent dipole moment. You talk about this in chemistry, dipole moments? Okay. So there are some molecules that have a permanent dipole moment, like, what's the classic example? That's 60% your body. Is it 60% or more? I don't remember. Water, right? Water has a permanent dipole moment. Okay. So it's also possible, even if it doesn't have a permanent dipole moment, to have what's called an induced dipole moment. It's basically on an atomic level doing the same thing as this charge polarization. So if you apply an external field, you can cause that the positive charge, which is basically rooted in place, the minus charge will tend to be pulled preferentially to one side, and of course it's going to be pulled to the upstream side. So this is what we call an induced dipole moment. You guys know about this in chemistry? Okay, good. So I'm just going to simplify the drawing. It's going to look like this. So there's basically, that's meant to indicate the nucleus, and then the center of mass of the negative charge is not coincident because of the external field. Now, if it had a permanent dipole moment already, it would rotate into this orientation. Yes? And if it didn't have a dipole moment, it would be stretched into this orientation, right? So this would be true for both permanent and induced dipoles would align like this in external field. So this is a broad category of different things that will behave in this way, is that they will orient in a certain direction when an external field is applied. All right, so let's take a look. That's the best that these can do. There's no mobility, right? They will go into this orientation either by rotating their permanent moment or by the dipole moment being induced. But there's no mobility, so let's find out what happens. So let's put in a neutral insulator. I'll apply an external field. And I will draw these oriented molecules. And I'm not going to do too many, but let me just do enough to make my point. I'm trying to draw the electrons, the negative charge on the left and the positive charge on the right with all of them. Now you may look at that and say, well, that just looks like normal matter, right? That's what all normal matter is. It's just a microscopic mishmash of plus and minus charge. But let me point something out. Normally, oops, I forgot a plus there. Normally, the orientations are all pretty random, but now they're not. We find that on average, the minus charge is on the upstream side, okay? So the analogy that I guess I can try to give you, right? Let's talk about the ice cream truck, okay? Ice cream trucks coming through the neighborhood, okay? And where do all the kids go? Running toward the ice cream truck. Want to get some ice cream, okay? Those would be like the minus charges that are mobile in the conductor, right? Like, I want to get over there. And there's a kid that is grounded, okay? They're not allowed to leave the yard. Well, which side of the yard are they going to be when the ice cream truck comes in? They should be looking forlornly over the fence at all the other kids going to the ice cream truck, okay? So that's what we have here. We have these electrons on a leash. They can't just go to the left, but you can find them to the left side of their particular atom, right? Does that make sense? Okay, so let me clear up some of the space here. we do still get charge polarization. You will still have a higher preponderance of minus charge on this side and positive charge on this side. So we have managed to have charge polarization still across the entire thing. So we have charge polarization. The only thing we have to recognize is that the mechanism is not by migration of electrons. Rather, it's just by reorientation. So there's been actually no movement of charge one place to the other. It's not like you had a bunch of minus charge slosh over to the side. And because this mechanism is what you have, you can probably guess that you're not going to get nearly as much charge polarization. Okay? So if we go over here, we say the insulator, does it participate in charge polarization? Yes, but not as much. It's inherently limited in how much charge can polarize. You basically only have access to the atoms that are already near the surface, right? You can't have any mass migration of electrons from anywhere from the interior. So that means that any phenomenon that requires charge polarization, this will participate as well. For instance, we said that if you charge polarize in a non-uniform field, you can literally get attracted to charged objects. Well, you can do that here too. The example I do with students in my lab is I have them attract little neutral bits of styrofoam peanut. You ever had a styrofoam peanut like stuck to your hand? Okay. The reason why is you have some charge on your hand, probably from rubbing it against something that's somewhere else in the triboelectric series relative to skin. Now you have a charge in your hand, and it can attract a peanut, which is neutral. Okay, can't get it off there. Okay. So styrofoam is basically, if you had to categorize it, it's more of an insulator than anything else. So it still participates in this. So when we said that charged objects can attract uncharged objects, that doesn't just hold for uncharged conductors. It holds for uncharged insulators as well. It might matter in terms of the degree of how well it's attracted, but all the same phenomenon does happen with an insulator. Okay? So let's see what else. Well, if we are limited in how much charge we can polarize, the process gets stuck somewhere about here. Okay? You can't charge polarize all the way down here until E net is 0. There's just not enough charge to polarize here. So the process stops somewhere about here. So there, you will have that E net is less than E external, but it's not able to be brought all the way down to 0. And so what becomes of one of these charges in the middle? That's what holds it in that orientation. That's what holds even the atoms in the interior, holds them in that orientation with the minus charge on the left side. It wants to be on the left side because that's upstream to E net. But I do want to point out that the E net that it's subjected to is smaller than E external. There is some shielding. You can't just polarize until you don't feel like polarizing anymore. It's inherently capped off. So we go over here. What happens on the inside of an insulator? Well, E net is smaller than E external, but it's not 0. And we call this partial shielding. So for instance, your average atom in the interior might, say, only be subjected to 90% or 80% or 60% of the external field. Why doesn't it experience the full brunt of it? It's because it's being shielded by all its neighbors. There is charge polarization. It's just that not enough to bring it down to 0. So for instance, if Dr. Megavolt had an insulating suit, that would not be good. Because even if you are shielded from a lot of the external field, let's say you only get 60% of the external field applied to you. If 60% of the external field is enough to kill you, then your you're dead, okay? So that means that partial shielding may be small consolation if you're slightly less dead than you were before, okay? So you may wonder if partial shielding has any use at all, in practical use. I've tried to give you some practical applications here so this doesn't get too abstract all along the way. For instance, I talked about perfect shielding. I talked about lightning rods. This, you'll have to hold it in your back pocket because partial shielding at this point seems to be useless. But when we get to homework number 4, we'll talk about partial shielding as a way to soup up a particular electronics component called a capacitor. So we will come back to that a little later, and you'll see what that's good for. Now, as far as the outside goes, again, same story. Everything that happens with the conductor happens with the insulator, but not as much. So if you're limited in your charge polarization, you're going to be limited in how much you can bend the net field perpendicularly. So here, what we just say is it's bent, but not as much. So the net field is going to somewhat bow toward the surface, but it has no obligation to meet the surface perpendicularly. Okay? All right. So that right there covers the net field inside and outside a conductor. Are there any questions on that before I move on to the last row? Okay. Yes. Yeah.
I'm sorry, so I was trying like to think back and forth between the perfect shielding and partial shielding. So the perfect shielding, is it because there's complete polarization, like all the negative?
It's not all of them, right? But what it is enough so that no more would want to go. Because these negative charges in a conductor are so free to do whatever they want. The only reason they stop doing anything is because they don't want to. So when enough negatives have gone over here that no more would want to go, that's when the process ends. Basically, once the electrons that have moved cause an E-induced that cancels off the external, then the rest of the electrons experience no field and so no force. So that's when it ends. But in the insulator, you can't just polarize until you don't want to polarize anymore. You have to stop at some point. And at that point, the induced field may take off a little bit of the external, but not the whole thing. So the net field will be weakened, but not weakened all the way down to 0. Does that make sense?
Yes, thank you.
Okay, so the last column, or last row, is something called charging by induction. So this is a process of charging an object that is very different in flavor than charging something by rubbing it against something else, the charging by contact, which we talked about before. So induction it has it right in the name. This has some kind of E-induced, of course. It's going to induce a charge polarization. And we don't actually have to touch the objects. So here's what we have. We have a, I don't know, let's say negatively charged object. So this will be object A. This is already charged. It could be a conductor, in which case that negative charge will live on the surface, or it could be an insulator, where it's going to live wherever. It doesn't really matter. The only purpose it serves is to be a charge. And with that, we're going to take an object B, which is neutral, and this one, I'll explain, has to be a conductor. Okay? And we're going to somehow create a charge on B without ever touching A to it. We're going to induce B to have a net charge. So here's how we're going to do it. You might wonder, what's even the point of having A nearby if it's not going to, if all it's going to do is sit there? But A is the reason why the charge polarizes on B. okay? So in this case, the electrons, you can find them, they are going to be on the right side. So of course, they repel from the object A, which is negative. So we have the charge polarizes. So that's step one of charging by induction. Charging by induction, step one. You want to bring A nearby. That's going to charge, polarize B. Now, B is not charged at this point. It's still neutral. It's just that the plus and minus charge aren't all mixed up microscopically where we need a magic little pair of tweezers to sort it out. We have macroscopic charge separation. So now that we have plus charges over here and minus charges over here, all we're going to do is we're going to grab these minus charges, throw them away, and then we're done. So how do we do that? What we do is we connect the object